cosmic maps and measurements. I picked this title because I think of all of cosmology is really a big exercise in mapping, as an exercise in measuring our metric. On the very, very largest scale is measuring our metric. It teaches about the topology of space-time, measuring how the metric has expanded, space has expanded over time. It teaches us about dark energy and measuring the fluctuations in the metric, perturbations around Friedmann-Robertson-Walker. Of course, on large scales, it teaches us about dark matter. And on galactic scales, it teaches us even more about dark matter. And on really small scales, it teaches us about other exciting physics, like black holes. So, we have lots of tools for measuring the metric in cosmology, and many of these observational areas have really exploded with fantastic data in recent years in a veritable Norrgårds boon, as we say here in Sweden. And I want to just first summarize what we've learned so far in broad brush before delving into more detail. So we've learned, of course, that over the 13.7 billion years since our Big Bang, there are two basic processes which have been important. The first is the expansion. Just the zeroth order, the level of a Friedmann-Robertson-Walker metric, it's expanded. Right? And of course, that's transitioned the content of space-time from being very dense, more rarefied, to being harder to cool. And it's been very, we heard yesterday about how one can measure using supernovae that expansion history quite nicely. The second process is the clustering, the transition from being smooth and boring early on to clumpy and interesting. And the way I think of the big challenge in cosmology is we both measure the expansion history and then measure this clustering as a function of both space and time. And from the dependence of the clustering on the scale, space, we can back out, like Lyman Page told us yesterday, details about what happened early on, created the seed fluctuations, inflation, probably. And from the way the clustering has grown over time, we can learn about the stuff, which is doing the gravitating, learn about the details of dark matter, neutrinos, etc., and also more about dark energy. So let's just first very, very briefly summarize our understanding of these processes in a rather pictorial form. So here's a supercomputer simulation from Benjamin Moore and his group showing both the expansion early on and the increase in clustering due to gravity on a rather large scale here, involving the progenitor of a large galactic cluster. It's a little bit hard visually to separate the expansion part from the clustering part there. So let us also just look at this in so-called co-moving coordinates, where the expansion is taken out, and you see very clearly how gravity alone can take something almost uniform and make it very clustered. The scale of string theorists in the audience is like the individual blobs here correspond to halos which may host an individual galaxy. And if we zoom in on this, and look at smaller scales, we get things like this supercomputer simulation by Matthias Steinmetz and his group in Potsdam, where you see from a top view here, the same thing as you see from the side view here. Again, as you run time forward, things get more interesting. We're again on a smaller scale here, so that here we have less than 1 million light years. First stars begin to form, more stars form, and we see the main lesson that's come out of this community, that galaxy formation wasn't something that just happened and then was done, rather an ongoing process, continuous buildup of larger and larger dwarf galaxies that collided with each other in a series of mergers. And by more detailed study of this, of course, one can learn a lot of interesting things, not just about how galaxies are formed, but about dark matter, whether the dark matter is really cold or a little bit warm, because it has a very dramatic impact on the substructure of these kind of systems. And if you look around us with telescopes today, we see that sure enough, the Milky Way halo is actually quite clumpy. You into stars as test particles to map out the gravitational potential of the Milky Way halo, effectively mapping out where the dark matter is and how clumpy it is on small scales. And I think we're going to learn a lot more about dark matter that way. Let's zoom in still more using a technique known as adaptive mesh refinement that Tom Abel and his collaborator Stanford and elsewhere have perfected, where you can go in by 12 orders of magnitude all the way down to the first stars. And if you keep zooming in and look at it, you reach now the size of a solar system, a gas cloud contracting under gravity as it cools off and dissipates away with energy, settling into a disk, getting so dense in the center of the disk that nuclear fusion ensues. And all the while, stuff has been clumping farther out in this disk, forming other spherical bodies, which are hidden from view, but become apparent once the nascent star here blows away the disk that it's formed. And sure enough, you would expect from this picture that all the planets would be spinning in the same direction as the sun is rotating, which is exactly what we see in our solar system. And finally, for people who here to work on string theory in areas a little farther away from us, physical observation, I just want to emphasize that if you keep zooming in, when I first heard about plate tectonics, I thought that 200 million years was such a long time, but it's with the time scales we're talking about, this is less than a few percent of the age of the universe. So our universe is really old. So that was a little 3-minute summary of how Stockholm got here, based on our latest cosmological understanding. Let's get a little more technical now and review some of these issues in more detail. So as we heard in detail from Lyman Page yesterday, the microwave background provides invaluable information about the state of things early on, and tells us that things were almost perfectly uniform. The fluctuation level back then was 10 to the -5, which is almost exactly the same as the density fluctuations from point to point in the air in this room. If I speak by this loud, you measure by this far from my mouth. And if you plot that, and this has been a fantastic year, of course, for microwave background, both because the field has gotten a lot of recognition and won medals, and a lot of people have gotten to go to Sweden, but also because new discoveries keep being made. Here's something I'm very excited about, which you may not have heard about from just 2 weeks ago. Kendrick Smith, Oliver Zahn, and Oliver DeRay do a very, very nice analysis of WMAP data, have detected gravitational lensing of the microwave background. This is something which we knew had to be out there. We know that matter bends light, and gravitational lensing, of course, has been detected for 8 years now in random places of the sky, where what you use to see if you have lensing is distant galaxies as a backdrop. You need some kind of wallpaper to see, and then you study how that wallpaper has been distorted by the light bending by foreground matter. Here you use the microwave background itself as the wallpaper, and what I think is the most significant thing about this breakthrough is not the measurement itself, which is only 3.4 sigma, but a proof of principle. It's not only a signal which we know is there, but it proves that even with WMAP data, it wasn't really designed to be able to do this. We can pull out a signal, and it means that in the future, with Planck and other experiments, this is going to be exactly the gold mine of information that we can hope for. So microwave background is a field where a lot of exciting stuff is happening. I'm going to say no more about it because you heard so much about it yesterday from Lyman. But this is what the density field of the universe is going to look like back in redshift of 1100 or so, according to the microwave background. You wouldn't even see the fluctuations on a linear scale because 10 to the -5 is so small. And then, of course, these fluctuations grew over time, as we saw in these animations, amplified by gravity, into something like we see around us today. And a very useful way to quantify this clumpiness, for extracting physics from it, is to just take this 3D density field and Fourier transform it. And then we simply measure the variance of that, which we have a fancy word for. In cosmology, we call it variance. Power, so the power spectrum is just the variance as a function of k in your Fourier space. And as you know, there's been enormous progress in the field in recent years in measuring this curve, the power spectrum, using a host of different techniques. And in 1999, it feels very recent to me because that's when I became a father. Not that long ago. And things were still a complete mess in terms of just measuring this curve back then. And then both the 2-degree PDF Galaxy Survey and then the Sloan Digital Sky Survey really helped clean up measurements sort of in the central decades of this plot. The study of galaxy clusters, function of mass and redshift also helps measure this. The cosmic microwave background gives very nice consistent results on these scales to how clumsy the universe is and pushes out much larger scales comparable to that of the observable universe. And then, again, as you heard from Lyman, it's really this spectacular, not only how accurate the measurements are and how well they agree with simple theory, but how quickly this has happened. Now, these other curves shown in green, yellow, and purple are all theoretical predictions that at least one person who I really respect as a scientist actually took seriously just some 5 years ago or so, or 7 years ago. And the fact that they're so totally off now from the measurements just a testimony to how good the experimentalists have been in pushing the measurements forward. And we can map again those measurements into this space, the black point there. Then on smaller scales, the so-called Lyman-Forest technique, gives us interesting information, and weak gravitational lensing further complements this picture. So we've learned a lot more about the clustering of the universe. Gravitational lensing is the field where I think the most exciting things still lie ahead. In fact, that's true for all of those different techniques. This is from a recent compilation by Munchie et al. We can see that there's a lot of data now from a lot of different groups, but there's still important challenges remaining here in understanding subtle issues, so EV mixing and source calibration and other things to get the amplitudes to really agree well. In other words, to get measurements where the error bars include all relevant uncertainties. And finally, I think the best in this plot really lies ahead, with both better measurements in all of these different techniques, and even other techniques. I'm going to talk a little bit later about 21 centimeter tomography as an example of a future technique, which I think will be really cool. What I'd like to do now is just very briefly say a little more about galaxy clustering, complementing what you heard from Bob Nichol yesterday. So Bob told you about how one can do great things by measuring the acoustic scale in galaxy clustering. One worry that I and many people in the field have had for a long time about using galaxies to study the clumping of the universe is that what you really care about is how matter is clumped. And what you get is how light is clumped, the stuff that you see. Right? And the relationship between these two can be quite subtle. One very important lesson I think we've learned now with these new massive data sets is that things aren't as bad as we feared. This bugaboo of bias turns out that as long as you stick on very large scales and look at galaxies of different luminosities, for instance, it's as simple as it could possibly be. Here I'm showing galaxies from the Sloan Digital Sky Survey in this range of luminosities. And here I'm showing a completely different set of galaxies, which are a little bit brighter, or more luminous. It's a different object, have nothing to do with each other. But if I flash back and forth a few times, you see, and this is as simple as it gets. They are not only, they trace each other beautifully, right? Which you can quantify mathematically. by saying that the simple linear biasing model is consistent with this data. The density field of one of these is basically just the density field of the other one times a constant. And the only difference is what's consistent with Poisson shock noise. So that's very nice. At least, and we showed this in Molly Swanson in the very careful analysis, showed that this works really nicely as long as you're on scale bigger than about 5 megaparsecs. And the larger scales you get to, the simpler things you get. 5 megaparsecs is about as far as the range of the sort of messy astrophysical effects, which are not governed by gravity alone. That's why one theoretically feels that this is quite natural. That if you look at things hundreds of millions of light years apart, it's only the gravity which would matter. And this sort of simple biasing, not surprising. So with that, if you take seriously the idea that you can really use galaxies truthfully to map out what the cosmic density field is, let me tell you a little bit about a big project which has been lots of fun working with my many known digital sky survey collaborators on. Bob Mitchell here. This is from a paper which just came out some months ago. And the idea of all of these analyses, of course, is you make a really accurate map of the density of the universe created by galaxies. And you compare that with the theoretical prediction. And you see if you can get things to match. And since the theoretical prediction depends strongly on how much dark matter you assume there could be and various other cosmological parameters, by requiring that they match, you get nice measurements of your physical parameters. So this new project I'm telling you about extends by about a factor of 10 the volume, effective volume that we were able to probe before with the Sloan Digital Sky Survey, with our sort of ordinary galaxies. But these luminous red galaxies that we're using now are much brighter and therefore visible at much greater distances. So if you look at the history of this field, so here's where we were 8 years ago. Here's where we were 7 years ago. Now on the same scale, you see, the error bars are very, very small. These are the latest measurements of this power spectrum curve here. A very good agreement with the theoretical prediction in red. And one thing which is very surprising is that with these luminous red galaxies, you can actually do much better with 60,000 of those than with hundreds and hundreds and hundreds of, in fact, 2 million or so of the ordinary ones. You get so accurate measurements that you can stop using this big log scale and multiply through by k and look in a linear scale, and you see, you start to then see the same kind of wiggles which are apparent in the micro background. And as Bob Nickel explained to you yesterday, for example, this scale here, exactly this acoustic scale, tells you these interesting things about how the universe has expanded over time. Why are these galaxies so useful that you don't need as many of them as ordinary ones? Well, basically, if you look at our observable universe here, on this same scale, you see all the galaxies that we have mapped before from the Sloan Digital Sky Survey, the normal ones, make up a tiny volume here in the middle, with green and yellow and stuff. So you're really limited by having a small volume, or by sample variance, as we call it in deep space. And so we want more volume. The red points here show these luminous red galaxies, so you have more volume. If you use quasars instead, would get still more volume. But then they're so sparse that you get completely dominated by just Poisson shock noise in your error bars. Whereas if you use ordinary galaxies, they're so dense that you're completely dominated by the limited volume. As Nick Kaiser showed decades ago, the optimal number density, if you have, someone gives you 1 million galaxies and you want to space them out so sparsely that the contribution from Poisson fluctuations is about the same as the contribution from sample variance. And we targeted these luminous red galaxies precisely for that reason. But they have this roughly this Goldilocks number density. And as you heard from Bob Nickel yesterday, this has been so successful that there's a follow-up project called BOSS, which aims to map these Goldilocks galaxies at still larger scales. more industrial style. All right. So I've given you a very quick summary of why I'm so excited by measurements, data, and cosmology. How in many different areas we've had a lot of progress in our ability to measure clustering in the universe, or for the function of space and time. So what can we learn from this? As I alluded to, of course, when you have all this data, you can fit theory to it. And you already heard yesterday, for example, how we can place nice sharp constraints and cosmological parameters from this. If you look, for example, at the two parameters which are very relevant to inflation, the density of dark matter and dark energy, you get a sense again of why I'm so excited about this, because only in 2003 the double map data finally was able to rule out all of this red stuff with 95% confidence. With the 3-year W map data release, all of this was ruled out also. So you could say, even from the micro background alone, the inflation prediction space should be flat. In other words, this plus this is 1. In other words, you got a diagonal. It was looking very good. If you combine this with our galaxy clustering measurements from these luminous red galaxies that I just showed you, all of this yellow stuff is also excluded. And we end up with a measurement of omega total with 1.003 plus minus 0.010. And that's very exciting if you're on relay day, for example, right? Because this is a theoretical prediction which was made back in the 80s. And even though, say, when I was in graduate school, many people thought that this number was 0.3. Right? And some people like Andre really stuck their gun and said, no, we still predict this. Right? And now, this is confirmed to about 1%. This is way more accurate than you can get out of any sort of anthropic explanation that I've seen. And I think it's very impressive. To give you one more example of parameter estimation for this recent data, if you look at the plotters, something which Lang discussed yesterday, also the spectral index versus gravitational wave amplitude. Here again, double map first year, double map 3-year, adding in our slow digital sky survey data. And what's so nice here is that there's been these theoretical predictions which have been lying around for decades, right? But what specific inflation models actually give you. And after waiting for decades, now finally, the data has gotten good enough that they started to bump up against theory. Theorists, experimentalists kept cutting their error bars by factor 2, but the sensitivity was way up there, so you weren't ruling out anything interesting, right? And then the first contact sort of basically made a few years ago with WMAP1. That was the first time that data got good enough that it really started challenging seriously some inflation theories people had written about in books and so on, like 5 and 4. And the data is going to keep doubling in the sort of Moore's law quality, its precision, year after year. Right? So very quickly, we can have a completely different landscape here, where most inflation models are ruled out, and maybe we'll even have a winner. For instance, the simple phi-squared model, which I'm predicting we'll hear more about Monterey later, it's needed, is still perfectly consistent with the data. And what's so exciting is the data is going to get so good that if you take Quant and the Sloan Digital Sky Survey, and everything works when it's completed, and everything works according to spec, and these are the sort of error bars you're going to get, right? So if this is the truth, so we're somewhere in this little black line, and everything outside of the blue circle gets ruled out by experiments, some people are going to get really excited. And I think it's important to remember this, that even though we don't know if inflation happened, exactly what the energy scale was, and so on, right? It's really quite possible. My guess is, this is my very, I mean, it's really quite possible that we will even detect these de-noise from inflation within just a few years. It all depends on what sort of theory we have, but I think it's quite plausible. And that would be very cool. We heard from Sten Hannestad yesterday about neutrinos, how one can learn very interesting things about neutrinos, also from putting together microwave background and galaxy clustering and so on. So I'm not going to dwell on that at all, because I want to spend a little bit of time looking towards the future. It's very tough to make predictions about anything, especially about the future. In the US, people like to attribute this to Yogi Berra, but I've heard it attributed to Niels Bohr also. If someone knows who published first, you let me know. In any case, this isn't going to stop me from making some predictions. First of all, it's very safe to predict that we're going to have more fantastic data coming along. Because in all of the different areas I mentioned, there are projects which are being built, which are being funded. The weak gravitational lensing, for instance, here is an ongoing thing, things which are going to happen within a year, and more iffy things. And the key thing to note here is when it's going for 100 square degree type of thing, vastly larger sky areas, it's going to get enormous precision out of that. In terms of map using galaxies, I already mentioned the BOSS survey after Sloan 2. It's temporarily falling here. And here there are also a number of other exciting projects either being done or being proposed. So I think we're going to, again, be in that field, being able to really blow away what we know so far. What's the ultimate goal? I started out by talking about new maps and measurements and how I think of cosmology as mapping our universe, measuring the metric. So ultimately then, of course, our goal should be to map this. And I don't mean just map the surface of this, which Lyman Page and his collaborators have done so nicely, but I mean map the whole interior of this also. And there's clearly a long way to go, right? So the microwave background has basically mapped a thin onion layer at the surface, and all the galaxy surveys we've done so far have mapped the dinky little bit part of the volume in the middle here. So what else can we do? In gravitational lensing, also is largely limited redshift below 1, at least at the moment. Microwave background lensing, like I mentioned, has just been discovered, ultimately has some sensitivity all the way out to redshift 3 or so, which is exciting. Line alpha forest is also good out there. But what about most of them all? Here is a very new technique, which I've spent a lot of time working on together with Angelica Costa and various collaborators. I'll show you in a moment. It's called 21 centimeter tomography. And it has the potential to map a large fraction of the whole volume, going all the way, going from redshift 7 and way up. So let me very briefly review what that is for those of you who aren't familiar with it yet. The idea is very simple. We know that there's a 21 centimeter line neutral hydrogen, which corresponds to whether there's spin alignment or anti-alignment in nuclear hydrogen, maybe like one of the protons. So you can look for this signal, but redshift at 21 centimeter. If it happens at the redshift of 9, then it's 10 times longer, 210 centimeters. So it's radio waves. It's like FM band, 100 megahertz, 200 megahertz, which means to build detectors for this sort of thing, you want to go as far as possible away from radios and cell phones. So this is a map of how much radio frequency interference you have in different parts of the planet. There are 3 experiments so far funded to do this. One of them, unfortunately, for political reasons, was forced to build it in Holland, which I think has the global maximum of cell phones per square kilometer. And there's one project in China called 21 CMA, having some political problems, and it's a little unclear what's happening with it. And finally, I'll tell you a little bit about this project, the Nura Wide Field Array, which is the one that I had the luck to get to be involved with, which is being built in Australia, which you see on this map. In the middle of Western Australia, it's very, very radio quiet. But nonetheless, relatively easy to get to. It's a collaboration between MIT, Harvard, and a number of Australian groups. And basically, the idea is to just build a gigantic radio telescope out there, but at much lower at these very low frequencies, like 100 megahertz, 80 megahertz, 250 or so. And it's a digital radio telescope we're building, so instead of building a monstrous dish, we basically put out very large numbers of these pylons like this, and then do all the correlating and things in a computer. You know that a big optical mirror can be thought of as doing an analog Fourier transform, in a sense. Well, you can do that faster in your computer these days, and cheaper in your computer these days than it would cost you to build a giant radio telescope. So you cover the Australian outback with a lot of antennas like this, and this is a technique which may completely fail. You know, it's in the same situation as the microwave background was maybe in 1990, when nobody had discovered, 1980. No, 1990, when nobody had discovered the fluctuations yet, right? 2 years before COVID. But yet, one knew there had to be microwave background fluctuations. Just like we know that there has to be this, because there is hydrogen out there, and we know that 1 centimeter line exists. Right? So instead, what you have are big challenges with understanding galactic radio noise, foreground, big challenges with engineering, trying to get the sensitivity down to the right levels. But just like I think there was very good reason to be optimistic about the microwave background in 1990, I think, again, it's the same thing here. Nobody has identified any showstoppers. It seems like it's going to be a lot of hard work to make it happen. And if you can, there's great science potential for fundamental physics. These sorts of projects have so far largely been funded to try to understand the epoch of the ionization, the epoch when the first stars switched on, and so on. But I think ultimately their greatest impact is just going to be on fundamental physics, mapping the cosmic density field throughout this volume. As you can see, redshift and hydrogen from all these redshifts. And this is just a little forecast that might be Mao did together with characterization. It's showing that you can, for some parameter, cosmological parameters, do up to a factor 20 better than from the Planck satellite alone. So it's going to be a really exciting thing to see how this goes. So in summary, it's been great fun to see how better data has so far translated into better measurements of cosmological parameters. And to me, the most fun part of cosmology really is the future. Is what do we do now that the data is going to get still better? I think there's plenty left to do, because behind each of the cosmological parameters that you hear discussed, right, lies a big mystery. For the dark energy, as we heard yesterday, we know how much there is. That's the only thing we know. We have a fancy word for it. But what is it? The million-dollar question here, of course, is it constant? Is it constant in time? Is it constant in space? And supernovae are making very nice tests as to whether it's constant in time. Things like micro background lensing that I mentioned also test whether it's constant in space. The early universe, we'll hear more about inflation at this conference, of course. So far, we've measured two numbers about it: the amplitude of fluctuations, 2 times 10 to the minus 5, and as we heard about from Lyman, the spectral index. But there's much more information out there to be harvested, which will give us quantitative clues to what happened. There's a very broad question. We measure all these parameters. 26 parameters you can do, dimensionless parameters. You can do the whole standard model of particle physics. With 6 more, you can do cosmology also. But with 32 parameters, you can explain every number we've ever measured in science. But where do they come from? And finally, for dark matter, I'm closing and finish with that, because I think that's perhaps the one area where you can see the fastest progress of all. It's been many years now since Vera Rubin showed us that there is dark matter by studying galaxy rotation curves, and Fritz Zwicky realized that there is dark matter from studying clusters. But there's really been a small revolution recently in our ability to learn more about dark matter using the same basic idea, gravity, right? Which is the only technique that so far let us probe dark matter, with a bullet cluster giving beautiful evidence that dark matter really can't just be dismissed easily as an alternative form of gravity of some sort. And I think right now there are actually as many as 4 roads to dark matter where you might see some progress on a timescale of 1 year or so. And we have the Large Hadron Collider, which is going to start taking data about a year from now, which might actually produce dark matter, if we're lucky. We have the GLASS satellite, which is being launched this fall, which may transform one of these tantalizing hints of dark matter from funky radiation from space into an actual smoking gun. And we have huge progress in direct detection from various groups around the world, pushing the sensitivities down, and not at all implausible that one of these groups is actually going to detect something. And as I already mentioned, on the gravitational side, it's also very exciting. So I think, in summary, there's good reason to be optimistic about the future of cosmology, and so the universe is a happy place for cosmologists right now. Thanks.
Question?
One on page promised that you are going to tell us about possible anomalies and maybe non-gaussianities, which are just shown.
Yeah, so there is this evidence of cosmic string in the doubly map data, and so in terms of non-Gaussianities and anomalies, well, so the first non-Gaussianity that was really established to be there in doubly map data is the so-called axis of evil, right? This fact that if you low-pass filter this and you look at the largest angular scale, there's weird stuff going on. The octopole and the quadrupole seem to be rather planar, which is a non-Gaussian thing, and they're aligned. And depending on how, when Angelica and I first wrote about this, we felt that we did a very quick analysis and concluded that maybe it was like a 1 in 60 fluke, this alignment, and 1 in 20 for the planar octopole, and 1 in 20 for the low quadrupole. So if you multiply that all together to be maximally conspiracy theoretical, you get 1 in 24,000 or so, which we didn't take seriously. But after we did that, a lot of other groups, Kate Lange, Omar Gejo, and Glenn Starkman, and many others, looked at that in much more detail, and a number of those people feel that it's actually more significant than we had found. On the other hand, there have also been a lot of people arguing that maybe something else mysterious is going on. I think it's still a very wide open question what's happening here. 4 possibilities, of course, are it's a fluke. It's something to do with foregrounds, but that does not convince me at all, because if you have foregrounds, there's no reason they should be correlated with the cosmic signal, right? So if anything, things like the low quadrupole, that should get worse if you blame it all on foregrounds. A small universe, we live in some kind of generalized donut, that could have explained the axis of evil stuff and also the low quadrupole, but it's been pretty much ruled out by failure to see these matched circles in the sky. And then finally, some sort of funny inflation, which is, there's been a lot of papers on suggesting. I think the jury is still out here. What's a little bit irritating is it's not that easy to get more accurate measurements on these largest scales, because WMAP is already sample variance limited. So one can go look at it in polarization, or one can look at the galaxy cluster quadrupoles and things like that. Maybe squeeze out a bit more information. And then there's, so that's large scale stuff. And then there's of course also been some suggestions of other things, but I think that's the thing I worry about the most. More questions?
You mentioned the cell phones and the galaxy and the politics as problems for 21 centimeter. Are you bothered by the solar activity at all?
Not so much. We have taken real data already from this site, and you don't see any problems associated with solar activity. Occasionally, we'll get a little blip from when some military satellite or so flies over. You can also get things like when there's a satellite, then radio transmissions from Perth bounce off the satellite and come down. But other things are way, way below even that. So I think this is, so far, it's looking very good.
More questions?